Hey, sorry about that.
No worries.
It's really unprofessional of me. I do apologize.
Oh, no worries, bro.
So let us continue then.
Yes, let's go. Let's see. Doesn't show the options for. Oh, there it is. Nice.
All right, so we are back on some stoichiometry. So I think we skipped number 1 in this section, and then we skipped 3 and then 4. We skipped quite a bit. So let's go back to number 1. I think that was the one that had molarity.
Yeah.
So this is the one we got 101.46. So yeah, that's correct actually. So did we have any questions about this? Did you want to go over one again, or are you feeling pretty good about that?
I'm feeling pretty nice about this.
Fantastic. So on to number 3. Now, this is the one that made me kind of nervous because I didn't remember anything about molarity. So I just researched it a little bit. And could you scroll up a little bit? I feel like we're going to need a little extra room for this one. So do you remember anything about molarity from your own chemistry class at all?
It has to do with molars.
Yes, exactly. So molarity is just a fancy word for concentration. So they have this 0.750 molarity, this M right here. That just means it's that many moles for every liter. So molarity just compares moles for every liter. So it's just going to be another conversion factor. So remember that whenever we're solving a stoichiometry problem, we have all of these different conversion factors. Whatever is on top is equal to whatever happens to be on the bottom in a single column like that. So this is no different. The only thing that changes is that we're going to have another column with moles on top and then liters on bottom. That's the only difference. So we want to start by writing the equation. No matter what kind of a stoichiometry problem they throw at you, that's always going to be the first thing you want to do. So we call this an acid-base reaction. So this is different than synthesis, different than double replacement, single replacement, all the other reactions we've had so far because of molarity. So molarity applies to acid-base reactions, but not any other kind. So let's start by writing the equation. I'm going to write it above. Let me increase the font size a little bit. So we have hydrochloric acid reacting with, oh, this is going to be 2, by the way. I balanced this already. We're going to have 2 of these in the balanced equation. And then we're going to have calcium chlorate. And they react to form calcium chloride and water and carbon dioxide. And then everything else is just going to be a 1 coefficient. So we have water and carbon dioxide. All right. So I want to identify what we have, and then I want to identify what we want. So I don't know if you're a visual learner, but I'm definitely a visual learner. I have to have things color-coded. And I'm looking at my old notebooks from school, and they look like rainbows. I have all these different color highlighters, and they just help my brain make more sense of the information. So how many liters of carbon dioxide gas can be prepared? So we have how many liters of carbon dioxide gas? That would be this right here. Can be prepared from excess calcium carbonate reacting with this many liters of this molarity hydrochloric acid. Hydrochloric acid is HCl, which occurs right there. So the blue and the red, mainly what that tells us is that we have a ratio of 2 to 1. So for every 2 units of hydrochloric acid, we're going to produce 1 unit of carbon dioxide gas. So that's mainly why I think it's pretty useful. So we want to take a look at what we have. So we have liters. and we're trying to get liters of something else. So we always want to start by writing what we have in our dimensional analysis. So we have 120 liters of hydrochloric acid. And then this next conversion factor is where we want to consider the molarity. I almost said polarity there. So it's going to be molarity. So it tells us that we have this many moles for every 1 liter of hydrochloric acid. So the molarity just becomes another conversion factor. So we have liters of HCl canceling with liters of HCl on the bottom. So our unit we have left over would be moles of hydrochloric acid. So what we need to do is we need to convert moles of hydrochloric acid to moles of carbon dioxide. And then when we have moles of carbon dioxide, we can convert that into liters of carbon dioxide. So sometimes it's useful to cancel things out before writing the next conversion factor, just so it's really super clear what you have to convert next. So we have this many moles of hydrochloric acid, and that happens to be blue. So we're going to have the blue coefficient, it looks like we have 2. So that's going to be 2 moles of hydrochloric acid. I want to stop me at any time if you have questions, if what I'm saying doesn't make much sense, all right?
All right.
Cool. So we have 2 hydrochloric acids for every 1 carbon dioxide. So we're going to put the 2 moles, in this case, it's going to be 2 moles of hydrochloric acid for every 1 mole of carbon dioxide gas. And then we're almost there. They're asking for liters of carbon dioxide. So we just have to convert moles of carbon dioxide into liters of carbon dioxide. So do you remember how many liters are in 1 mole of anything?
The liters are in 1 mole, I believe 100 or 1,000.
Oh, well, you're thinking of milliliters to liters. So there are 1,000 milliliters in a liter. But if we're comparing moles and liters, there's always going to be 22.4 moles, no, 22.4 liters in 1 mole. Doesn't matter what it is. In every ion, every element, every atom, every molecule, it's always going to be 22.4 liters for every 1 mole, no matter what it is. So now let's make sure the units cancel. It's always a really good idea to check. Moles of hydrochloric acid cancel. Moles of carbon dioxide cancel. And we're left with liters. This is liters of carbon dioxide. I forgot to put the molecule name there. So now we just have to do the math. So we're going to do 120 times 0.75 divided by 2, and then times 22.4. And I get, this would be 1,008 liters of carbon dioxide. But, let's see if it won't let me annotate anymore. Oh, there we go. All right, there we go. Any questions?
Nope.
Cool. All right.
CO2.
Fantastic.
Let's go.
All right, so we had an answer for 4, but I know you wanted to review that one anyway.
Yeah,
so let's talk about number 4. So I want to identify what we have, and I want to identify what we want. But first, we want to have, oh, they gave us the equation already. And I don't remember if it's balanced. So we have 6 chlorines and 6 chlorines, 3 magnesiums, 2 irons, and 2 irons. Yeah, cool. We are balanced. So we have 41 grams of magnesium. Oh, and then this is going to be a reaction where we have 2 different masses of 2 different products given. So this right here is 41 grams. And then our iron, we have 175 grams. And then, oh, it's doing this weird thing where it doesn't hold space. It doesn't hold the tabs.
Doesn't hold the tabs?
Yeah, I hit tab a few times, and it looked like it gave me a few tab spaces, but then I hit enter, and then it just got rid of the tabs for some reason. So it's always something. Zoom's always doing something weird. So we have this many grams of magnesium and then this many grams of iron 3 chloride. So a really good step to do in a situation like this is always to convert to moles. So I want to convert our 41 grams of magnesium into moles. So the molar mass of magnesium is 24.305 grams per mole. So then if we divide, we get 1.687 moles of magnesium. So now we want to do the same thing for our other reactant. We have 175 grams of iron 3 chloride. So the molar mass of iron 3 chloride is 162.2 grams per mole. So if we do the math, we get the following. We get 1.079 moles of iron 3 chloride. So now that we have the number of moles, we want to figure out what would be the limiting reactant. So the way we do that is by comparing them, because right now we have different quantities of moles. We have 3 moles of the first reactant, we have 2 moles of the second. So we can't really compare them just yet. So what I want to do is I want to take this number right here, the number of moles of iron 3 chloride, and then I want to multiply it by a certain fraction that will allow me to compare it with this, because right now we're comparing apples to oranges. We can't really do that. We really want to be comparing apples to apples. And in order to compare apples to apples, we have to multiply this by the stoichiometric ratio that would make them equivalent, because 3 of this to 2 of that, they're not equivalent. We need them both to have the same coefficient. So we have 3. Well, so we want to divide by what we have. So this is iron 3 chloride. What's the coefficient in the equation? If you look at the equation, look at the reactant iron 3 chloride. What is the coefficient of that?
Iron 3 chloride. Well, that is 175 grams, right?
Yeah, that's 175 grams, but what's the coefficient in front of the compound?
Oh, I see. And the coefficient is 2?
Exactly. So this is iron 3 chloride. Iron 3 chloride has a coefficient of 2, so we always divide by what we have. And then we always multiply by what we want. So we want to compare this to magnesium. Magnesium has a coefficient of 3, so we're going to multiply by 3 and divide by 2. So this is how we compare apples to apples. So we have this times 3/2. We get 1.618 moles. And we had iron 3 chloride, but after doing this conversion, we multiplied by 3/2. We're now dealing with moles of our other reactant, moles of magnesium. This many moles of magnesium is what we have. So now this is really useful information. Now we're able to figure out which one is the limiting and which one is the reagent, the limiting and which one is the excess reagent. So,
yep.
we want to compare this figure right here with this one. Oops, I meant to make this into the thing we're missing, iron 3 chloride. So we have less of this than we do with this. So we have 1.618 moles of iron 3 chloride. We have 1.687 moles of magnesium. So we have more magnesium, which means magnesium is going to be the excess reactant. And then the iron 3 chloride is going to be the limiting. And then they want us to figure out the mass of iron produced when the reaction is complete. So in a chemistry class, whenever you're given mass, you should automatically think grams. They're asking how many grams of iron do we need? So the first part of the problem dealt only with reactants, but this part of the problem deals with the product because iron is going to be a product. We want to figure out how many grams of this particular product result from these conditions. So we want to convert our number of, we want to figure out how many moles of iron we have. So I think we should take, let's see here, what should we do? So this right here, this 1.681 only refers to, actually, hang on a second. I think there's an easier way. I'm always on the lookout for an easier way to do something.
Yeah.
Oh, I'm erasing a bunch of stuff I didn't mean to erase. Here, I'll just do the math again. So 41 divided by 24.305, 1.687. All right, this many moles of magnesium. So then we want to compare magnesium with iron this time. So magnesium has a coefficient of 3, iron has a coefficient of 2. So we want to take this number of moles, we want to divide by the coefficient we have, which is 3. We want to multiply by the coefficient we want, which is 2. So we're going to do 1.687 times 2/3. And we get, hang on a second, 687 times 2/3. We get 1.125. And the units there are going to be moles of iron. And we're almost done. They want the mass, so we want to find how many grams that is. We have moles of iron. We want to figure out how many grams are in 1.125 moles of iron. So we need the molar mass of iron. Which happens to be 55.845 grams per mole. So then we're going to multiply the number of grams we have by the number of moles we have. 55.845 times 1.125. And we get 62.826. This is grams of iron. So we've answered everything they wanted us to answer. We found out that the limiting reagent is iron 3 chloride, and the mass of iron produced is this many grams of iron.
Nice. And for our final question, 50 grams of sodium metal was reacted with 39.5 liters of chlorine gas. If sodium metal is limiting reactants, how many liters of chlorine gas remain in excess than the reaction is complete?
So we have to balance first. We're going to have 2 of these, and then 2 sodium chlorides, and then bam, we're balanced. So we have sodium metal. That's the quantity that we are given. That is 50 grams. And then we have a number of grams of chlorine gas as well. Actually, that is in the liters. So sodium is the limiting reagent. So it's always a really good idea to put everything in moles first. So we have 50 grams of sodium. We want to convert that into moles. We need that molar mass of sodium, which happens to be 22.99. 22.99 grams per mole. So we're going to do 50 divided by that number. And we get 2.175. And our units are going to be moles of sodium metal. So now I think we want to do the same thing with chlorine. So we're going to convert liters into moles this time. So chlorine, we have 39.5 liters. And then there are 22.4 liters in every mole. So we have 39.5 divided by 22.4. Any questions so far? Good on everything?
Yep.
Fantastic. So we get a result of 1.763. And then the units are going to be moles of chlorine. Sodium metal is the limiting reactant. How many liters of chlorine gas remain in excess? Then the reaction is complete. So we want to find the stoichiometric ratios first. So I want to take this number of moles of sodium, and then I want to multiply it by that ratio we have. So we can tell by the equation that the ratio of our 2 reactants of sodium to dichlorine is going to be 2:1. So because we have sodium on top, if we're converting, we want to put the number of moles of sodium on the bottom. So this would be 2 moles of sodium underneath 1 mole of chlorine. So then moles cancels with moles. We're going to take the number of moles of sodium and then just divide that by 2 to get our result. We're going to do 2.175 divided by 2. We get 1.0875.
0.0875. Yep.
We're not quite finished yet, though. That's just the number of moles of chlorine we have. Oh. So we need this information to figure out how much remains in excess. So we're going to be comparing this amount right here with this amount. So to find how the amount that's in excess, we do the excess reactant minus the limiting reactant, the number of moles of excess minus the number of moles limiting. So our result is going to be liters in excess is equal to 1.763 minus 1.0875. And I'll find out what that is real quick. We get a result of, my computer is acting weird again, get a result of 0.6755 moles in excess. Oh, hang on a second. Sorry. We need to convert this information back to moles to get the number of moles of that. We have to convert it back to liters, excuse me, to get the number of liters in excess. So I'm going to take this number of moles of chlorine. I'm going to convert that into liters. So this is going to be this many liters for every mole. $24.36 liters of chlorine. And then we want to do the same thing. Sorry, this is turning out to be a really long one. So we found out how many liters of chlorine there are in the final result. We want to do the same thing with, actually, hang on, this was sodium right here. We want to do the same thing for chlorine. So I'm going to do 1.763 times 22.4 to get the number of liters. So this many moles is equivalent to 39.4912 liters. Almost there. This is turning out to be a big doozy of a problem. So number of liters in excess is going to be equal to the number of liters of our excess reactant, 39.4912, minus the number of liters in our limiting reactant. So we're going to subtract 24.36. And let's find out what that is. So we get a final result of 15.1312 liters in excess. So that right there is our final answer. That took a while. All right, so was that it for today, or was there anything else?
Well, that's really it.
All right. Well, let me know if you need help with algebra. I'm happy to make any videos if you need any algebra things cleared up. And just let me know. You have my number. Just shoot me a text if you need anything, okay?
Will do, Chief.
All right, good luck on the test. I'll see you next time.
See you then. Bye.